Welcome to lesson number 3 of the course on industrial automation and control. So, typically drift is characterized for temperature and time. Now we come to, so this more or less completes our static characteristics. So, generally talks about an input output curve, right, that is a calibration curve. So, there is no time here. If we give an input, we will get an output in the steady state, and we are only talking about the characteristic between this input and the steady state output value, right. But we have to talk about dynamic characteristic of the instrument when the input is not steady. So, the input is continuously changing, and the dynamic response of an instrument to an input signal is typically modeled in terms. So, now we have to worry about that if a signal, if the input signal suddenly changes from some value to some value, how is the output signal going to change? So, we are not only concerned with the steady state, new steady state value that the output signal will achieve, but we are also concerned with how it is going to achieve that over time. So, when we talk about such characteristics, we talk about the dynamic characteristics of instruments. So, accordingly we have various kinds of instruments. So, we start with the simplest, which is the zero order instrument, whose characteristic is given by y equal to kx. So, it is assumed that for the kind of inputs that are relevant to that sensor, the output is instantaneously equal to the input. So, it is like a resistance, you just apply a voltage, you immediately get a current. So, the input output ratio is linear, and this linearity exists from instant to instant, right. So, it is a, so for such instruments there is no dynamics, and the static characteristic is the only characteristic that you need to see. So, such instruments are called zero order instruments. For example, typically, a potentiometer, I was talking about a resistance, right. So, a potentiometer is nothing but a resistance. So, for a potentiometer, the position signals, potentiometers typically measure position, so the potentiometer will be connected to this variable point. So, as the variable point moves, the voltage that you will get will be directly proportional to the position, right. So, in this case there will be instant to instant, and since the position is actually a mechanical variable, so therefore there is not going to be too fast a movement. So, as far as, so the electrical behavior is so fast compared to that you can just assume it to be a pure resistance, and then you have what is known as a zero order characteristic. So, the output voltage will be directly proportional to the displacement theta, let us say angular displacement. In this case, if potentiometers can be angular as well as linear. So there is a sensitivity called of the potentiometer is volts per radian. On the other hand, there are some kinds of instruments where if the input changes suddenly, the output cannot change suddenly, the output takes some time to rise. For example, let us take temperature measuring instruments, for example, a thermocouple. Actually, a thermocouple is typically, as you will see, it is not, wherever it is making the measurement of the temperature, maybe it is steam, then the bare thermocouple is actually not inserted into the steam, because that will damage the sensor, it will degrade fast. So, it is actually put inside a tube. So, you can imagine that even if there is a temperature change outside that tube, which is called a thermo well, so it is a tube, inside that you have the thermocouple. So, even if your ambient your environmental temperature which you are trying to sense, even if it changes, some time will be required for this temperature to actually flow through the, that is, there has to be heat flow through the insides of the thermo well into the thermocouple junction before an EMF can be developed. So, because of the thermal properties of this thermo well, there is going to be some time required. So, even if you suddenly fill this space with, let us say, steam, the temperature of the junction will not, junction of the thermocouple will not instantaneously be equal to the temperature of the steam, but it will slowly rise, right. So, for such transducers we have a first order instrument character, first order or second order. So, that will depend on the modeling of the thermocouple. But so typically first order instruments are transducers that contain a single storage element and can be modeled of first order. So, for such cases the output value actually obeys some kind of a differential equation which is of this type, and where tau is called the time constant of the system. So, if tau is larger, then the system slowly rises, while if tau is short, then the system is fast. So, we can easily compute the response of a sensor whose input is a step input. So, let us try to characterize the response of this kind of a sensor to various kinds of changing inputs. So, these are two examples, mercury glass thermometer and thermocouple in a thermowell. So, if you have a step input, so the first kind of input that we consider is a step input. So, step input means it is at 0 and then suddenly it rises. So, at t is equal to 0, the input is 1, suppose. So, then we can compute that the time response or yt is going to be such a function of time. So, the graph will show what kind of a function it is. So, you see that it will gradually rise and then it will become 1. So, if you have a large tau, it will rise slowly. If you have a small tau, it will rise fast. So, this is tau decreasing, right. On the other hand, as we all know, I mean, the response to a dynamic sensor to arbitrary inputs is of interest, because if such a sensor is actually put in a control loop, all kinds of it is not going to be regular as a step input. So, we sometimes, since we know that any arbitrary waveform, most arbitrary waveforms can be thought of as a sum of sinusoids, sine and cosine waves. So, it is very useful to actually characterize the behavior, that is the response of the instrument to a sinusoid of different frequencies. So, this is called a frequency response, and this is very important for an instrument. So, if we have a sinusoid, so this is my instrument. I am applying an I sin omega t. Typically, what will happen is that if the instrument is supposed to be linear, then you will get, as output also you will get a sine wave, but that sine wave magnitude will be higher, will be different from the magnitude of the input wave, and it will also develop a phase lag. So, it is this. So, we actually try to study two things. Since the frequency is going to remain constant, so the frequency need not be studied, it is the input frequency itself, but the ratio between the output magnitude and the input magnitude, which we call the gain, and the phase lag. These are the two things that we typically characterize. So, this is a mathematical solution. So, for example, the gain over different values of frequency actually varies like this. So, you can understand that if the frequency is too low, then the gain of that is 1, because so the frequency is too low means you are giving a slow sinusoid, which means that the instrument can always come to steady state and it can get the value of the input. On the other hand, as the input frequency increases, so before the output of the instrument can really rise, the input changes. So the output of the instrument can never rise enough, and therefore the gain falls. So this is the frequency characteristic of an instrument. Similarly, if you have a phase plot, then it turns out that as you go for higher and higher frequencies, the phase lag increases, and the maximum phase lag possible for a first order system can be 90 degrees. So, it will gradually approach 90 degrees. Now, sometimes we also have to model the systems as a second order instrument or sensor. This choice can actually depend on which kind of model you will use. That may depend on physical reasons, or it may depend on the kind of response that you actually get from the instrument. So, some instruments are rather assumed to be governed by a second order differential equation, for example, accelerometer, anything which has mass spring damper kind of representation, and we will have second order dynamics. So, its dynamics, its input output dynamics is given by a second order differential equation as shown, in which there are two parameters, one is called a natural frequency, another is called a damping factor. So, again its response to the step input, in this case we have three kinds of cases depending on what is the damping factor. So, one case is when the damping factor zeta is greater than 1, in which case we call it an overdamped system, and this is the expression for the output time function. We will just see the case and then we will see the plots. So, and then we have a case when xi is equal to 1, zeta equal to 1, which is called the critically damped case. Here we, and the last case is when we have xi is less than between 1 and 0. So, that is called the underdamped case. So, the plot actually looks like this. So, this is of interest to us. So, you see that this is the step response. So, the input applied is this is the input. Now, for different values of zeta, for example, if as zeta goes to lower and lower values, you can see that you get an oscillatory behavior. So, there is an overshoot, this is called an overshoot. So, for underdamped sensors you are going to get an overshoot. On the other hand, for overdamped systems there is no overshoot and it slowly rises just almost like a first order system. Similarly, if you see its response to a sinusoidal input, again you will find that these are the expressions. So, you get a gain and you get a phase shift, and this is the expression for, this is the plot for gain. So, you see that the gain actually changes with frequency, right, and for underdamped systems the system tends to resonate. So, this is the resonant frequency. So, if you give a sinusoid close to the resonant frequency, then you get a huge output, right. Well, on the other hand, for overdamped system there is no such resonance. So, you have similarly the phase, if you see the phase, the phase plot looks like this again with frequency. So, towards low frequency the phase tends to stay small, and as frequency increases, so the maximum phase that can occur is 180 degree. So, these are the phase lags. So, we have seen the static and the dynamic characteristics of sensors. Now, let us see some example specifications. So, this is for example an industrial thermometer. So, see what it says, what all are stated. So, first of all it is based on a thermocouple, therefore, the type of the thermocouple is stated. We will see what the type of thermocouple is, but interestingly the range is given. So, you see this is the minimum and the maximum values in which this thermometer can be used with these given specifications. So, if you use it within this range, then you will get a resolution of 1 degree Fahrenheit or 1 degree centigrade, and etc., etc. So, whatever specifications are given are valid within this range. So, in this case range is 1370 and span is 1440. The resolution is 1 degree F or 1 degree C, actually it is whichever scale you use, because actually the resolution of the basic sensor is the same, while actually it is depending on the scale that you choose, you can have different kind of electronics. So, the resolution also varies. So, it says that the resolution, so here it is stated as 1 degree centigrade. So, it is, so the minimum change that can be observed, which can be detected by the sensor, is actually 1 degree centigrade. calibration error standards. So, all these specifications are actually with respect to a certain, this DIN is actually the German standard, BS is the British standard. So, similarly, it says that the meter accuracy at 25 degree centigrade, that is when the ambient temperature is 25 degree centigrade, is 0.2% of reading plus minus 1 digit. This plus minus 1 digit comes because you are going to have a digital display. So, we see that in digital displays there has to be there is an effect called quantization, and therefore, this plus minus 1 digit error comes. So, basic accuracy is 0.2% of reading. So, in this case it is stated as in terms of reading. There are some other, apart from these kind of specifications, there typically if you see an example industrial specification, you will find some other things like which are specific to the which are specific to the particular sensor that you are using. Now, since thermocouples use long wires, so there is a series mode rejection. Series mode rejection means that typically when thermocouples are drawn from long wires, so they typically tend to catch series mode interference, especially at the power frequency, because there may be power lines and they will add power frequency interference as a series voltage. So, it says that the sensor is so constructed that it can actually reject that 60 hertz such voltages which are induced. Similarly, zero drift, it says that even if the zero drifts, every time possibly this instrument will have a button, and or maybe every time this instrument is commanded to take a reading, it will first automatically make it 0. So, so there is an auto zeroing facility. The environmental temperature range is, so there are all these specifications are to be, this sensor is to be used in such a range, and the size and weights. Okay. Similarly, another thermometer another temperatures thermometer, again based on thermocouple, again it has some ranges. So, we have already seen it. Look at its accuracy reading. It says that below 230, so you see that below 230 degree Fahrenheit, above minus 150 degree centigrade, this is its accuracy statement, while below that this is its statement. So, here it is stating it in terms of reading, here it is stating in terms of a constant or a percent of span. Similarly, it says that in some other mode called a differential mode, this is the kind of accuracy, plus minus 0.3 degree centigrade over a plus minus 100 degree centigrade span. So, you can see that typical such industrial instrument specifications will include this kind of parameters. For example, resolution is 0.1 degree, and above 999.9 degree it is 1 degree. The other things are battery housing. These are specifically, battery is important, especially when you have a portable instrument. So, let us look at another sensor, which is a flow meter. There are so many specifications. The important ones are, say, accuracy and linearity is plus minus 1% full scale. Here you see accuracy and linearity are both plus minus 1%. Possibly the instrument is inherently linear. So, therefore, they are stated together. See, repeatability is stated as plus minus 0.2% of full scale. That means, even if you make 100 readings of the same flow, the readings will not differ by more than plus minus 0.2% of full scale. Similarly, you have say inherently linear, flow signal is inherently linear. Therefore, accuracy and linearity are specs, both are same. Actually, if it is not inherently linear, then accuracy and linearity specs will actually vary. So, then there are some special other specifications which are specific to a flow sensor. For example, pressure drop is very important, because the pressure drop in the flow sensor is actually an energy loss. So, it should be low. So, it says that approximately 4 inch H2O. So, the other factors we will not understand so much unless we really know what sort of a flow meter it is. So, this brings us to the end of the lesson. So, what we have done in this lesson is that we have seen why sensors are so important. We have also seen their general structure. We have looked at the static characteristic, main static characteristic parameters, and like sensitivity, linearity, accuracy, resolution, span, etc. We have also looked at the dynamic characteristic of 0th, first and second order instruments, and we have seen that they exhibit phenomena like oscillations, overshoot, they have time constants, and all these characteristics are very important, especially when these devices are used as feedback devices in control. We have also seen some industrial specifications. So, before closing, we would like to have some points to ponder. So, for example, what is the difference between accuracy and linearity? So, when are they same and when are they different and why? What is the difference between dead zone and resolution? Which is likely to be more, dead zone or resolution? Then mention 2 performance parameters of control systems that are directly affected by sensors. So, and finally, what is the significance of damping in a sensor? So, if you have good damping, what kind of sensor should have what kind of damping? For example, what should be the damping of an indicating instrument, and what should be the damping level, let us say, for a recorder, or what should be the damping level for a let us say a feedback sensor. So, think about these, and that is all for today. Bye bye.